Good afternoon, everyone. It's a pleasure to have with us Professor Kwan Nguyen. So Kwan is a professor at USC. Before that, he was a postdoc at MIT. So welcome back. And before that, he did his PhD from Carnegie Mellon and won the Best Dissertation Award. Kwan's work has been Kwan has been working on a lot of cool things, and the most recent videos I remember are humanoids running in sand, which was very cool to watch. Kwan's work has won, multiple, best paper nominations. And also, recently Kwan became chief scientist of Motion, which is a humanoid company coming out of, Vietnam, the largest private company, I presume, in Vietnam at this point. So it's exciting to have, Kwan with us. And, I'm looking forward to what you have to say about Legged Robots. So please take it away.
Okay. Thank you. Thanks, Phuket, for the introduction, and thank you for having me. It's my great pleasure to be here today, and it's very special for me to come back and present at the MIT Robotics Seminar. About 6 years ago, I was a postdoc here at MIT, and normally in the audience, right? So it's always a very big dream for me to have a chance to present as a speaker here at the seminar. So thank again for the opportunity. So for my talk today, I'm very excited to talk about our research on hierarchical learning and control for agile and adaptive legged robots. So basically, I will talk about different research projects in our lab to enhance agility and adaptation for legged robots. And during my presentation, if you have any questions, feel free to interrupt me at any time. So to start my talk, please allow me to go back in time and share a highlight of my work here at MIT. So when I was a postdoc with Sang-Bae Kim, I had a chance to work with this mighty MIT Theta 3 robot. So until now, with even a lot of development and commercialization for legged robots, but I think this is still the most powerful quadruped robot that ever existed. However, when I joined the lab, the robot was able to walk quite well, but not able to jump yet, right? So the task that Sang-Bae gave me that, okay, you need to let it jump. It's quite pity if we cannot let this powerful robot jump. And here we go. And this is actually the video that's captured from Sang-Bae phone using the slow motion. Okay, so that's a good memory. Earlier this day, I have a chance to visit and meet with the MIT Cheetah robot again. But there's one more video related to this that I really would like to show here to the audience. So this is a compilation of some failed experiments that I got along the way before getting the successful experiment that I showed you earlier. Hopefully it's great. Okay. 3. Okay, I have many more videos, but I just want to show a couple of them. So the message that I want to show here that I know that some of you here in the audience could be the PhD student or postdoc, right? So if you happen to get stuck with your experiment, don't worry, right? This happens all the time. And that's how we do reinforcement learning for research, right? We keep trying. If it fails, let's learn and improve over time. Okay. So come back to my talk talking about the motivation for my research. Let me first play this video. So I feel pretty lucky to find this video because as you see later on, this represents very well different projects that I will be presenting today. So in this case, as you see in emergency response, our first responder just barely walk, right? They just run, use their hand, use their entire body, to climb faster and at the same time carry very heavy load or equipment. So they need to deal with lots of heavy lifting tasks. And they need to do it very quickly, as fast as they can, because of the urgency. Okay. So for this, I want to highlight here this about dynamic local whole body local manipulations because they do a lot of local manipulation tasks, but you need to leverage the whole body to perform this task very effectively, right? And the second part here that they need to adapt to different load carrying problems and they also need to adapt their performance for challenging terrain. Okay. And these actually three main capabilities of legged robots that our lab has been trying to achieve in the last several years. Okay. So I hope the video I showed earlier can somehow provide some good reasons why legged robot can be helpful. And in my opinion, legged robot can soon help replace human in many meaningful applications. But I believe that the key features that we need to have to achieve this level is agility and adaptation. Right? Without agility and adaptation, we would not be able to have legged robot in some practical application. And to tackle this challenge, we have been working on a different problem and solution to improve agility and adaptability for legged robots. And these different topics that we have been working on. And today, I'd like to highlight three main different research topics in our lab that I will try to present today. Okay? And I would like to show some quick videos, highlight here so that you can have a big picture of our work. So firstly, I will talk about our work on MPC for dynamic locomotion and local manipulation for both quadruped robot and humanoid robots. And then secondly, I will present our work on adaptive control for legged robots that allow legged robots running while carrying an unknown heavy loads or interacting with unknown objects. Yeah, so this is a video for this, one of the video for the second topics. And lastly, one interesting question that we are trying to address in our research is how to leverage reinforcement learning to realize long-term agility and adaptation. Okay, so before explaining in more details our research, let me give a quick overview of model predictive control for legged robots. So this is basically the baseline approach for many other works that I will be presenting today. So as you see in this video, the MIT Theta 3 robot with MPC controller can blindly climbing up a stair with one single controller. Is very robust to this uneven terrain. Okay, and in this video, it's totally blind. So there's no camera, no prior information of the stair, but the controller can handle it pretty well. So this is a very nice framework, right? It's very robust to uneven terrains. You can simply use one single MPC controller to achieve a wide variety of different locomotion gates and velocity command. However, it also has several limitations. So what is the limitation, right? So to better explain it, let me try to talk a little bit about the control diagram for MPC here. So here, as you see, there are two main components for MPC, for legged robot. The first one is the force control. When we have the legs on the ground, we do force control. We regulate the force command to the ground. Okay? And the second component in this control diagram is swing control. So for force control, we optimize ground reaction force at a stand fit, but we do a single rigid body dynamics because it allows you to have a linear MPC model so that you can solve it effectively in real time. Okay? For the swing foot placement, it's important because it helps you to do step-by-step stability. So basically, when you take a step, it also helps you to balance the body. Okay? So what's the problem here? So firstly, as you can see, for MPC for quadruped robot, it's initially designed for quadruped locomotion only. So here in our talk, in my talk today, I will talk about how can we expand MPC for local manipulation. Okay, and the second disadvantage of this because we need to use a simplified model to guarantee that it can be solved in real time. But because of that, it has some problem with model uncertainty. So in the second topic, I will talk about how can we use adaptive control to address this problem. Okay? And this last one is that as you see in the control diagram that I showed you earlier, there are two components, stance and swing, right? But there's two controllers that kind of decouple from each other. So later on, I will try to present another framework on reinforcement learning so that we can better synchronize between these two components, or better have a more unified framework to modify them at the same time. Okay. So firstly, let me talk about our work on adopting MPC to realize dynamic local manipulation on Lekka tablets. So from this figure, I would like to show an overreaching idea of our vision or application for local manipulation in this domain. Okay. So, and in this different application and different figures that I want to show here, there's three main kind of challenges that I want that we focus on addressing. The first one is how can we coordinate smoothly between locomotion and manipulation so that the robot can perform local manipulation effectively, right? And then the second one is how can we optimize not only the interaction force, but also the contact location. So during the interaction with the objects, the contact location for the local manipulation task is also very important. And the last one it's pretty critical for local manipulation, because as you see in many applications here, we don't know about the object's parameters, right? We interact with the object the first time. So it's important for you to be able to adapt to a wide variety of unknown object parameters. Okay. So for the first projects that I would like to talk about in the direction of local manipulations, I want to present these projects. So the motivation for this is that you may see some work on manipulation, in-hand manipulation, right? But if you have a very large object, it might not possible for you to use a hand to do manipulation. So in this work, we use the entire robot body to manipulate this large and bulky object. Okay, so let me try to explain the framework here. So in this framework, we have a principle of hierarchical MPC when we have two different layers of MPC controller working together here. So the first one is a contact optimizer MPC, right? So what does that mean? So it means that you try to optimize for the contact force and the contact locations that apply to the object. So here we have two control variable, which is FC and D1. So we optimize for this. Okay, so we want to make sure that this contact location D to be within the side of the box, okay, of the object, and the contact force within a range that it can handle. Okay, but one important thing that I want to highlight here, that we optimize for a sequence of contact location over time. As you see, we have D1, D2, up to a longer horizon. Okay, it's important because later on we will use this sequence of decision making in the next layer of MPC that we have. Okay, and then the second layer of MPC we call local manipulation MPC to regulate the desired contact force and contact location that we have in the first layer of MPC. Okay, so the principle here that we have now, let's say if we assume that the robot pushes the object with a contact force FC, it also means that you have another force that applies to the robot. So using this knowledge, you will try to design the controller for MPC so that you can regulate this contact force FC, and also you use distance or the contact location to define the motion of the robot, right? The desired motion of the robot. Okay. So as I mentioned earlier, we not only use one contact of the variable for one contact force and location, but we leverage the sequence of them. So basically, we want to care about what you want to command in the future horizon. And it's important for MPC, and you put in the MPC controller, and you so forth. Okay? So this is some comparisons that we have. So for example, if we have a baseline locomotion MPC controller, it fails because it don't regulate the contact location. The second method is that we use heuristic policy for contact location. but it cannot really control the orientation and position at the same time, right? Because you have one single box, you have a robot, now you want to steer to control position and orientation at the same time. If you don't, so now for this example, the importance of the prediction in the future show up, okay? Because on the right here, let me maybe play it again. On the right here, because we know the prediction horizon in the future, so the robot can try to compensate for both the error in orientation, position at the same time, okay? So it's try to make adjustments so that eventually it meets both position and orientation at the same time. Okay. And we also successful conduct experimental validation for our method in this experimental setup. Another interesting experiment that I want to show here is that here the robot needs to push the box, but at the same time it also needs to avoid this obstacle here. So it requires accuracy in manipulating this obstacle. Okay. Any questions so far? Okay. So for the next part is, let me continue with local manipulation, but now let me talk about local manipulation for the humanoid robot. So for the first part, we kind of expand the MPC framework for our bipedal robot. So the concept is quite very straightforward, very similar. We have the structure very similar to what we have earlier for MPC, for quadruped robot. The only key difference here that we have a different model for humanoid, right? So in humanoid, instead of having contact force only, we also have a moment that can be regulated in the contact point. So with this simple kind of modification, but it's worked quite effectively. So using this method, we was able to realize very robust and agile locomotion on our humanoid robot Hector. Okay, and we also test this with different. Here we have locomotion, we have turning, we even have turning on uneven terrain. Okay, and we have our simulation open source here. If you want to give it a try, please go to the link and try it. And recently we also brought Hector to Mars. Okay, just kidding. So we brought Hector to a NASA event in Mojave Desert in California, where the terrain is considered very close to Mars. Okay, so we have a lot of fun, but the weather at that day was quite extreme, right? So we there are a lot of winds, and it's very hard to run the robot during this day. But we have a lot of fun. We run the robot almost like 6 hours continuously without any problem. The robot fails sometimes. Later on, you will see some failed experiment at the end. But because of the size of the robot, the failure is quite minor. And we just bring the robot back up, reset, and run it again. I'm not sure if you can hear it, but the wind is very strong. Okay. Okay, so next I would like to talk about our method on dynamic local manipulation. So this may be related to some of the your work, Phuket, about throwing objects. Okay, but we try to do it with humanoid. So let me first show the video to highlight what we are trying to achieve here. So as you see in this video, the robot pick up a 2-kilogram object and try to throw it. And as you can imagine that, let's say, if you don't consider to the object dynamics, right? If you simply throw the object forward quickly, it will push back the robot and it will fail. Okay. So what's the principle that we have here? So the main principle that we have here is there's two different things. The first one is we need to consider the object dynamics inside the MPC model. But the second one is also very important, that we need to consider the context sequence that we have in the local manipulation task. So as you see here in this multi-contact sequence model predictive control, we have contact for the foot, but we also have contact sequence of the arm with the object. Okay. So talking about the model, that's one interesting finding that we have here. So let me do some quick comparison to talk about this. So that's, let's say if you're holding an object, right? And you want to design a controller to manipulate it. There are three different options that you may have in mind. The first option is that, okay, let's say if you ignore the object, okay? You consider that the robot stays the same. It's obviously it will fail, right? Because you don't consider the object in the dynamics, and it failed, okay? But the second method seems to be very straightforward. Is that okay? As long as you have an object, okay, you just put the object to the body, and then combine them, okay? That seems to be the most straightforward way to do it. But when we tried it, it failed, okay? Why did that? Because the thing that now you don't keep the object all the time, right? Sometimes you have the object on the table, you want to pick it up, and then you put it another location. So it means that you expect the change in the object mass or structure in the controller formulation, okay? But what happened when you combine? It means that at the time that you combine, you significantly change the formulation of everything you have in MPC. Because you change the mass, you change the center of mass location, so that's significant change in the MPC formulation. And eventually, the optimization problem will not be able to give you a good solution for that, okay? And then the third option is basically the common ground between them. So you represent the objects as an external force, okay? So if you represent the object as an external force, it means that when you have the objects, you only have one single kind of parameter that appear in the formulation of MPC. Okay, so let's say if you pick up the object, you release it, there are minor change in the MPC formulation, and it works very well. Okay, so it means that the conclusion that we have this final choice and represent the object as an external force. Okay, so it's obviously this option will be more accurate, right? More straightforward, but this is work better when we combine everything together. Okay, so this is also kind of highlight the meaning of hierarchical structure. When you have hierarchical structure to perform different tasks, right? Sometimes you need to certify the accuracy because when you put everything together, right, it needs to kind of synchronize with each other well. Okay, and then using our method, our robot can perform this dynamic local manipulation quite well. I think our students have some creative idea that they have the battery instead of the load. Okay. We run out the load in the lab and we put it there. Okay. Before I move on, any question on this topic? Okay, go ahead.
So when you represent the payload as an external force,
Mm-hmm.
You talk more specifically about the difference in that compared to value
Mm-hmm.
of it's not representing some like inertia term?
Yeah, so that's a good question. As I mentioned, it's obviously the second option will be more accurate, right? Because you mentioned you have like moment of inertia, something like that. But I think maybe one extension is that you can also have another term, like moment of inertia, to represent if you try to do something more in 3D space. Okay. Yeah, but I mean, if you just try to combine the objects, it changes, as you see in the MPC formulation, when you change the center of mass location, it changes every equation inside it, right? Okay. So for the second part of my talk today, I will discuss another light-up work on adaptive control for legged robots. So until now, I have been talking about different projects when we have local manipulation when we handle objects. But some of you may think that, okay, the assumption that we should not note about the object's mass, moment of inertia, friction, right? Because normally we don't have it. You have an object in front of you, you will try to manipulate it, okay? So it's what does that mean? So it means that in practical, you want to have an adaptive controller framework so that you can handle this wide variety of different objects and assumptions. Okay. So before presenting the adaptive control work that we have, let me talk about this, the motivation here. So as you see, we have force-based control, we have MPC for electric robotics work very well. But the current adaptive control framework is from the control theory side is normally for trajectory tracking, right? So what does that mean? So it means that for robotics, if you have you need to have different trajectory for different motion, okay? And that is, so in this framework, we want to leverage adaptive control, but for force control, so that we can have different advantages of force control that we have earlier. So for the interest of time, I won't be able to go into too details, but let me try to explain the main principle of the method here. So our adaptive control framework is based on the structure of model reference adaptive control. And here we compare the performance of our controller from the real robot and the reference model, okay? So the real robot here, we have, let's say, the robot carrying an unknown load. So this load is not unknown to the controller. And in the reference model, it's more like a simulation of the robot without carrying any load, right? And the root of the adaptive controller, that it will compare the difference between the state that it gets from the real robot and the reference model, so that it can design an adaptation law to compensate for it. Okay? But one kind of important thing that we need to kind of modify and adjust so that we can apply this force-based control for adaptive control for force control is that we need to kind of synchronize the foot position from the real robot to the reference model. Okay? Because in the reference model and the controller for the robot, we don't have swing control here. But if you see earlier, we have swing control for both. Okay? However, if you also implement the swing control in the reference model, there will be a significant difference between the two. But the road here that we want to adapt for the force-based control only, right? So what does that mean? So it means that you need to modify the reference model using the foot position that you get from the real data. Okay? So that's the main principle that allow us to do adaptive control using force-based control. Okay? And another kind of challenge when we apply adaptive control, especially for MPC, is because MPC is very computationally expensive, right? And now if you need to run two different MPC controllers, and you also need to run an adaptation law, so it means that it's very complicated computation happen on board, right? So what does that mean? So it means that in order to make it happen, you need to have this kind of adaptive frequency framework to make sure that everything can be run in real time. Okay? So as you see, there's several differences between the frequency here. For example, for the reference model, you want to make sure that it's accurate enough. You run it in 1 kilohertz, right? But for the reference MPC, because you just want to compare with the real model, you can allow this to run it at a lower frequency, okay? You satisfy a bit of accuracy, but you can make sure that, okay, everything can be run at, in real time. Okay, but for the real controller, let's say the red one, that's the real controller for the robot. Because you run the robot on board, you want to make sure that this is run fast enough. Okay, so you need to run at higher frequency. Okay, so when you combine everything together, running at different frequency, sometimes you need to certify the accuracy of the controller. But putting together, you have an optimal performance for the framework. Okay, so here's some, let me play it again. Here's some comparison. Let's say if we use conventional MPC controller, it failed with only 3 kilograms of load, but without adaptive MPC, it can carry up to 5 kilograms. Okay, and if you take a look at the plot for tracking here, the error is almost 0. Okay, even with 5 kilograms of load. Okay, and another interesting case here that even when we design the controller, we don't intentionally design for compliant terrain, right? But because of the adaptation, when we intentionally test with a case that we haven't done before, and because of the adaptation, it's allowed the robot to adapt to this in real time. Okay, and we also validate our controller in a wide different scenario, different terrains. This one is for on a slope, carrying also 5 kilograms of load. One more video that I really like, that we are able to achieve fast running while carrying 5 kilograms of load. As you can see here, when the robot speed up, the water here actually shaking a lot. Right? But as you see from the video of the robot, this can keep the body stable very well. Okay. So to continue my talk, I will talk about how we extend our adaptive control framework for local manipulation and collaborative local manipulation. So this come back to the example that we have earlier. Let's say if we have a large and bulky object, right? You would not be able to do in-hand manipulation. So one option is that you can use a body to push the object. And another application is even, let's say, if the object is very large, right? So normally you need to have multiple human or multiple robot to work together on this. So in this example, we assume that, let's say, if we have very large object, so what's the assumption that we don't know? So we don't know about the mass, we don't know about the movement of inertial, we don't even know about the center of mass location of the object, right? But Z parameter is normally very important for you to design the controller or to perform the task. And this is a control diagram of our methods. So as you can see, the main principle of this method is to decouple the control framework into 3 different control layers. So that's why we call this hierarchical adaptive control. So here we have layer 1 is used to design an adaptive controller for the entire system, right? So basically, you consider the objects as an object that you want to manipulate, and you have different control input applied to this object. And so in this first layer, you don't worry about Bauer-Lehrkes robot, right? You design a framework so that you can manipulate this object using different control input that apply to this object. And in the second layer, you use it's used to distribute, right? So you distribute this different force and contact location using a QP-based control for force distribution. And then for level 3, we will execute just local manipulation controller command from this, the second layer. Okay. So using this method, as you see, if you don't have just local manipulation MPC, the robot gets stuck because we don't have the object in the dynamics. Here we have this our adaptive control framework activate, and it can push the object with the desired velocity. It's another experiment that I want to show here. So in this experiment, there's some interesting kind of unknown factor that we have here. So we have the slope. So this is also unknown to the controller. We have the object, we have friction. These parameters are totally unknown to the controller. And you see the robot just stepping normally, and the student that put it in front of it, and it's kind of almost immediately adapts to push this off. And yes, it's another work when we do with collaborative local manipulation. So we expand it. So now we have two different robots, right? We have one A1, one alien row, so two different robots working on the same problem. But because our method is very generalizable, so we can just treat different robot as a different kind of actuator to apply to this system. Sorry, let me stop this a bit. Sorry. Okay. So another work that I want to talk about here, that we also expand our framework, but here we also use vision-based and footstep planning. Okay. So let's say if you do collaborative local manipulation, you carry a load together, heavy load together. But what happens when you have complex terrains? You have stepping stone, you have obstacle, so you need to coordinate with each other so that you can complete the task. See if I can play the video. Sorry. Let's wait a second. Let's see if I can play it again. Okay. So as you see here, along the way, the robot will do footstep planning. So there's a gap here. You try to adjust a step. But as you see, if you have one single robot planning only, right? So let's say if you don't coordinate with each other, it's very easy to fail in this case. So that's a very challenging problem. As you see, if you carrying a sofa with your friend, for example, right, stepping upstairs is a very challenging problem. You need to be careful. You need to plan for it. Here, the robot also need to adjust the height so that it lift up the obstacle so that it can avoid it. Okay, and we was able to realize this on a simple setup here. Let me see if I can play it again. There's too many video in one slide. It gets stuck. Sorry. Yeah, so for this experiment, what we try to do is that we have two robots carrying this object, but one needs to adjust the height so that it step over this block. But at the same time, it needs to make adjustment in the body. It may not be clear here, but it needs to raise the height a bit so that this object does not collide to the obstacle. Okay. So for the last section, let me talk briefly about our work on hierarchical reinforcement learning to achieve long-term adaptive behavior for legged and humanoid robots. So firstly, I would like to talk about our work on RL augmented MPC so that we can better synchronize stand and swing control in the MPC framework. Right? So as I mentioned earlier, in our MPC framework, there's two different controller, one with stance and one with swing, but they're decoupled from each other. So here we want to leverage our reinforcement learning framework so that we can synthesize force control and swing control, right, to improve agility and adaptive behavior for legged robot. Okay, and the principles that we have here that we have it's basically, I will explain it further, but we have a term that's called dynamic compensation to do adaptive control. So let's say earlier when I talk about adaptive control, we have a load carrying problem, right? But when we do that, basically it will reflect in some change in the dynamics equation, and this policy will try to learn this acceleration term. So this is the acceleration term. or first command. Okay, and later I will explain the reason behind this equation. Okay, and using this framework, we achieve quite significant improvement in terms of agility and adaptability for Leggett robot. So to be more specific, we can increase the turning speed up to 58%, right? We can do load carrying up to 80% of the robot weight while navigating this compliant and unstructured terrain. And in the last experiment, it's quite interesting that we can also handle blind stair climbing with swing foot reflection, right? Because we have we change the swing control over time using reinforcement learning. So whenever it gets stuck, it kind of automatically reflects and swing over the stair. And another interesting advantage of this approach is that we can have zero-shot sim-to-real transfer to not only one robot, but across different robot platforms. So what does that mean? So it means that we train everything in simulation using this A1 model, right? This is A1 robot, this is Go1 robot, this is the Alien Go robot. Okay? So we train everything in simulation using the model for A1 robot, but then we will be able to transfer it to not only A1, Go1, but also Alien Go, which kind of twice bigger than the other two. Okay? And I believe that the reason behind it is that we have two different key elements here. Firstly, we embedded MPC inside the reinforcement learning framework. Therefore, the robustness of MPC allow very good sim-to-real transfer, right? But secondly, the key thing here is, as you see in our framework, we have this acceleration term, right? So this acceleration term kind of representing the physics of the problem. It say that, okay, any kind of uncertainty from the physical world can be represented by an acceleration, right? And as long as you divide it by the mass of the robot, it can be scalable to different robots, right? Okay, so that is a reason why we can, our framework is kind of generalizable for robots of different sizes. Okay, so for the interest of time, let me go quickly for the last part that we have here. So here we have our work on what we call Oracle Guide multi-mode policy that allow learning multi-mode locomotion effectively from a very raw reference motion. So the key idea behind this is that we firstly learn latent mode representation for each control mode. For example, we have walking, hopping through a gap, jumping on a box, and we will roughly define some reference motion. And this reference is very rough, and you don't even satisfy any kinematic constraints or dynamics at all, right? But this reference can be used to learn a low-dimensional latent representation for each mode. And this latent mode can be used as an Oracle guide in training, which allows us to learn a policy that can achieve a wide variety of different locomotion modes. Okay? And then secondly, thanks to this mode encoder here, the framework can enable smooth transition between different modes. So that is important because you may learn different modes separately, but the question is how can you achieve a smooth transition between them? Okay, and with this framework, we have this pretty nice parkour motion. Hope you can see the video clearly. Okay, so here we have different modes of hopping, walking, standing, jumping up, jumping down, right? But as you see from the video, when we combine everything together, we have very smooth transition. Okay. As you see from the previous video, we also have backflip. We also extended for riding a unicycle. So of course, it's not easy to transfer this skill to experiment, but hopefully we can get there soon. Okay.
Was there a lot of work in defining the cost function?
For what? Okay, good question. Yeah, so I think for the currently for the current work that we have, I think it's also require a good amount of work for the reward turning. But we're also developing another work when we kind of refine the problem, when we pay more attention to the tool manipulation. So I think one of the problem when we transfer skill between, let's say, locomotion to another task is that we pay too much attention to the locomotion task, right? But let's say when you have bicycle riding or riding a skateboard, you need to pay more attention to the tool on the vehicle that you are riding. So this is another work that we're working on to make sure that the reward shaping problem or the structure, right, this can be more generalizable for the problem that we will address. Not demonstration here, right? Okay. So, all right. So that's all I have today. So before ending my talk, I would like to thank to all my students who have contributed to all the results that I have in the talk today. There's one more slide. In my lab, for my startup, we're actively hiring. So if you have any friend or you're open for position, please feel free to reach out to me. For my startup in VinMotion, we have office in Los Angeles and in Vietnam. That's about good location, right? If you want to consider, happy to discuss more and happy to connect. Okay. Let's see. Okay. Thank you so much, and I'm happy to answer any question you may have. Thank you.
Any questions from the audience? Do you mind using the microphone?
Thanks for the great talk. I have a question about this gate sequence. I see that like in a lot of quadruped in your video, that the gate sequence is quite fast, and you're talking about this adaptive control stuff. I'm wondering if you like considering like adaptively change the gate sequence or this context sequence. Yeah, the comment.
Very good question. Actually, we have another work called Adaptive Gate Frequency MPC, but because of the time, we did not have chance to present it here. But one of the applications that we have that, for example, we have humanoid robot doing stepping stone, right? So, but the foot placement also affected by the stability as a problem. It's obviously if you want to actively change the step length, you don't want to keep the same step frequency, right? So that's another work that we have when we try to actively adapt to the gate frequency. But that is also requires a prediction ahead of time. Because for MPC, you need to have prediction, right? This means that you need to make the decision. If you make the decision in the gate sequence, you also need to have it in the prediction horizon as well.
Do you apply that in your current framework, or?
Yeah, I have another work, but I did not have
Okay,
to
okay,
present
okay,
it here.
okay. Thank you.
Yeah, I need to reduce a lot of content. Yeah.
Also from my side, thank you so much for the talk. It was really interesting. I was really impressed by what you can do essentially with a blind robot adjusted depths. Have you thought about adding any form of perception and how that would help in your frameworks?
Exactly. So, for as I mentioned earlier, one of the work that I have. So in the IL augmented MPC framework, we want to show that let's say because one of the problems here that even with perception, right? Sometimes you don't have a good perception even with a stair. Sometimes you get stuck, right? And for example, if you have a robot walking on a tall grass field, right, even with perception, it may not have when the robot gets stuck. So we may want to see that, if the robot gets stuck, how can you do some reflection, right? Because so that is the motivation for the agricultural application. But as you see in one of the work that we have here, for example, right? So this is really required perception here, right? Because let's say if you go upstairs for the video that I showed earlier, if you have one single robot, you might be fine, right? But for two different robots working together in this complicated constraint, this is really required perception.
Great, thank you.
So one question I have is, Kwan, going back to the unicycle one, what do you think it will require to transfer that into the real world?
Okay, I think that's a very good question. So as you see, I would say that it's not only the unicycle one, but I would say that for one of the main problems for Sim2 Reals is also state estimation, right? So in simulation, basically you know everything. But in experiment for humanoid, for legged robot in general, you don't really have a good estimation for your body, for example. Joy may be okay, right? You have encoder, but the state estimation for your body is not really good. In this case, in training, you may have some information about your tool or the vehicle that you are riding here, right? But it's obviously in experiment, you don't have any information about it. You need to leverage, your own sensor, right, to estimate or field it. So I think that's an interesting thing that I think is related to some of your work as well. Right? In manipulation, how can we leverage the sensor or the motor of our own robot arm, right? So that you can feel the environment and you can manipulate it well. Because we don't have any state of the object can be measured directly to you, right? So I think that's a challenge not only for this one, but any, humanoid, legged robot manipulation in general. You don't really have a good state estimation to transfer everything.
Great. Any last questions? No? So let's thank the speaker once again.
Thank you.